I've talked about how we can set up an experiment using ideas from diffraction and interference that we learned from the ripple tank experiments to observe interference in light. So what I'm now going to do is to try and find a way to calculate for example, the spacing between these fringes. If I know, say, the distance of the screen, if I know the distance between the gaps, and if I know the wavelengths of light. Such calculation is important so that we can, if we actually do an experiment and observe these fringes, we can measure the spacing, for example, and check that we have that our idea is correct, that our idea that about these interference fringes is correct. So in order to do this, we first need to find a way or a formula to actually do this calculation. Okay. Let me start with thinking about, say, a particular points on the screen. Let's say that point where I have a bright fringe. Now, this bright fringe must have been formed by light coming from each of these gaps and meeting here and interfering constructively. So I'll just draw a dashed line to show the path of the light. So there's a light coming to this point, light coming, meeting at the same point. And we know that in order for constructive interference, in order that they add constructively, the difference between those two paths must be a whole number of a wavelength. Now, okay, before I go any further, let me put in some numbers just before this gets too abstract. Suppose that I set this up so that the spacing, right? Suppose that I have a piece of paper and I cut two little holes or 2 little slits, one here and one there, at a spacing of, say, 1 millimeter. So that's 1 millimeter. And the gap here, if you're actually cutting out a slit with a pen knife, it's actually not easy to cut a very narrow slit. So let me just say that this might be maybe 0.1, say 0.1 of an mm, or maybe a bit more. So about that. And let's say the distance from here to the screen is 1 meter. Let me take that as 1 meter. Now, how about the wavelength? The wavelength of the light. Let's say the wavelength of the light. Okay, I'm going to take it as 500 nanometer. Now 500 nanometer is the wavelength of green light. That's green light there. And that looks red, but I'm just going to take 500 for example. Okay, so suppose that we can actually set this up, okay, and we observe some fringe patterns. Now I want to calculate, I can actually measure it, of course. I can measure with a ruler, but if I observe it, what are the spacing between the fringes? But I also want to be able to calculate it from these numbers, right? From these numbers that I set up and the wavelength, to check that my understanding of this explanation about the interference is correct. So how can I calculate the spacing from these numbers? Right. So we start with this idea that the path difference, the difference between these two lines, is a whole number of a wavelength. Now, in order to make use of this knowledge, what I'm going to do is this. I'm going to say that, right, this distance, okay, this distance is much bigger than this. How do we know that? Okay, that's 1 millimeter, right? And that's 1 meter. 1 meter is 1,000 times longer than 1 millimeter. And that means that this distance is a lot smaller than this distance. Okay, so I've drawn this spacing in an exaggerated way. All right, this looks quite big. This doesn't look that small compared to this. But if I actually set this up, this distance would only be very small. And so those two lines are going to be almost parallel. They're going to be almost parallel lines. Very, very small spacing. So this means that if I draw a perpendicular from there to there, if I draw a perpendicular line to here, okay, then this distance would actually be the difference between those two lines. Okay, because since this is nearly parallel, both of these angles would be almost right angles, right? This would be approximately a right angle as well. Approximately. So this would be very close to the difference between the two lines. And this distance has to be a whole number times a wavelength. Now, I'm going to make things simple. I'm going to assume that I'm going to take this point to be, let's say, the first fringe from the center. Okay, so that's supposed to be the center fringe. That's the first fringe. That's actually the first fringe, but I've drawn it at the second fringe. But suppose I take this to be there. I take this point to be at the first fringe. Then that means that when this point is at the center, it is at the same distance from the two gaps. So the path difference is 0. But as I move away from the center, right, this path gets longer, and when the path difference increases from 0 until it's 1 wavelength, I will get the first fringe, right, from there to there. When I get the first fringe, is because the path difference has increased from 0 to 1 wavelength. Right, in between, we know that at half a wavelength, we'll get disruptive interference. So I'm going to try and calculate the spacing between the center and the first fringe, and that's when the path difference is 1 wavelength. And the spacing that I want to calculate, okay, from center to the first fringe. Let me try and label that. I'm going to draw a horizontal line from between the gaps to the center fringe. And I'm going to call this distance from here to here, I'm going to call it X. Okay. I'm going to call this distance D. Just give it some symbols so that it's easy to make a formula. And I'm going to call that spacing between the gaps A. So I have X, D, lambda, and A, and hopefully I can find a way to calculate X from B, lambda, and A. So let's press on. Now, the next thing to do is this. Look at this triangle here. I now have a right angle triangle formed by this side on this and this imaginary line and this path. Okay. Now the next thing that I want to do is to draw another triangle. I'm going to draw a triangle with this as one side, with this as one side, and the other side would be here, from in between the gaps to the fringe. So I like to look at this triangle, this one, okay, and this triangle. Now I'm going to show that this very small triangle and that very big triangle are actually similar triangles, meaning that all the angles are equal. So I'll start with this angle. It turns out that this angle, which I'll call theta, is actually very close to this angle here, which is also theta. Now this is actually quite hard to see, so what I'm going to do is I'm going to draw this part out here. Draw it out here. So I have, as this side, I have A. So that's my side A. Okay. And I have this side. Okay, let me draw the two dashed white lines first. So I have those two lines there. Those are these two lines. Now I have this horizontal green line. This horizontal green line. Okay. I have this blue line there. Blue line going there. So I'm just copying out this part and magnifying it. And I have this green line here. So that's a right angle, and this is a right angle. And these lines are parallel. Okay, so these lines are parallel. So what I'm saying is that this angle is the same as this angle. Now, you can hopefully see this more clearly now. This angle, if I call this angle theta, okay. Now, in order to relate it to this angle, what I could do is this. I could draw a line parallel to this. I could draw a line here. So if I draw a parallel line to this, then this angle is the same as this angle. Okay, this is also theta. Right? But we know that this is a right angle because this is horizontal, this is vertical. this is actually a right angle here. So which means that if this angle is theta, this angle must be this angle, this side of the triangle, must be 90 degrees minus theta. And since this is a right angle triangle, so that angle must also be theta. So therefore, from here we can see that therefore that this angle theta between the horizontal and the line going to the fringe, this angle is actually the same as this angle here between this vertical side, alright, between the joining the two gaps, and this slanted line, okay, that is perpendicular to the line going to the fringe. Okay, so we have shown that those two angles are equal, and this is the thing. This is the thing that allows us to connect the numbers a and lambda, which is around the gap, in between the gaps, with x and d, which is between the fringe and the gaps. So how we can do it is this. If you look at this triangle, therefore, and this triangle, you can now see that they are similar triangles because both are right angle triangles, right? That's a right angle and that's a right angle, and both have another common angle, which is this theta and this theta. So because they are similar triangles, the ratios of the corresponding sides must be equal. Now what does this mean? Corresponding sides means that like these are the corresponding angles, right? That's theta and that's theta. Corresponding sides means, for example, that this is the longest side of this right angle triangle. So for this one, this is the longest side of this right angle triangle. This is the longest side. Now let me call this side L. Okay, so the side L corresponds to the side A because both are the longest side of their own triangle, of its own triangle. And this is the shortest side. This is the lambda, corresponds to the x. Okay, so let me write this down. The corresponding sides for the small triangle, for lambda in the small triangle corresponds to x in the big triangle, and the longest side A in the small triangle corresponds to the L in the big triangle. Small a corresponds to the big L, and the ratios of the corresponding sides are equal because they are similar triangles. Okay, it's fine, but I really like to relate it to D, the distance between the direct distance, right? L is a slanted distance. But what I can say is this: because this distance is quite big and I expect the fringe spacing to be quite small, so therefore L is actually quite nearly equal to D. Okay, you can see that this line, the line L and the line D are quite close together. Alright, so L is slightly longer than D. But if this distance x, the fringe spacing is quite small, right? If the angle is quite small, then L will be quite close to D. So I can say that approximately that lambda over A, that approximately L is equal to D. So you can write this as x over D. So now I have a formula that relates these two. And with this formula, I should be able to find x if I know lambda A and D from these numbers, right? 1 millimeter, 500 nanometers, and 1 meter. So let me do this now. Right, I want to rearrange this. To make x the subject. So x would be lambda over A times D. So I'll try and calculate the x here. Okay, so x would be approximately lambda times d. Multiply both sides by d, right? So lambda d over a. Lambda d over a. Okay, and lambda we know is 500 nanometers. So 500 nanometers is 500 nanometers. Just write it out. Times d is 1 meter, and a is 1 mm. So 1 meter divided by 1 millimeter. Okay. Now milli is 10 to the minus 3, nano is 10 to the minus 9. So just put in those two factors. Just put those in and we'll find an answer that is 0.5 millimeter. 0.5 millimeter. So it's a very small distance here, but 0.5 millimeter we can just about measure. Okay, just about measure with a simple ruler, at least roughly, and we should be able to see with our eyes. So these are the kind of numbers and size of distances that we expect to see if we actually carry out this experiment.